Hello. Okay, everybody. Welcome to Thursday afternoon. Thanks for joining me on the live lecture for this afternoon. Let me go ahead and share my screen and we can get going. All right. So, I guess it's kind of an interesting week. Welcome to week number 5 in the semester. I think if I remember right, PSU was open on Monday and then we'll be open tomorrow, I think is what the email said. And hope everybody's been able to stay safe, kind of enjoy maybe a little bit of time off with the winter weather. Um, and so we'll see if next week we can get back to a little bit more normal type of schedule there. And so, even though the PSU's campus is closed right now, I figured I kind of made the call before PSU closed to switch over to a remote lecture. So, thank you, of course, for allowing me to have that flexibility. It ended up working out pretty good for this week, just considering that campus closed today. But just because of the nature of our class, we're kind of a hybrid class. We've got a lot of students acting remotely. I thought we could go ahead and actually have class as usual. So again, thanks for the flexibility. Thanks for understanding. We'll kind of hopefully get through the lecture tonight fairly easily. A couple of main things to talk about tonight. One is to expand our breadth of applications that we're looking for in terms of the application of linear programming. And then also, I do need to touch base with you guys a little bit about your first exam. If you look at the schedule, you know that we basically go through the first 5 chapters, and then we have our first in class or in course exam, so to speak. And I'll toward the end of the lecture talk about the structure of that, how it's going to be administered, and all those kind of things leading into next week. And so, with that being said, let's go ahead and hop into the actual main event of the evening. So we're in chapter 5. Chapter 5 is really a continuation of what we talked about last week, just applications of linear programming. They do say advanced. Maybe some of the notation I use is a little more mathy, so to speak. But I wouldn't really consider these too much more difficult, so to speak, than the applications we looked at last week. I think they're about the same level of difficulty or complexity. So don't be too scared off by the chapter title here. And so I've already got my Docker container up and running for the class. From the root directory here, we're in lecture, linear programming. Last week we were in LP Apps 1, now we're in LP Apps 2, which has the textbook materials in here. So I will just go ahead and start off by running the notebook. And if you can see, we're going to have a little bit lighter lecture compared to last week. If I remember right, last week I was getting to down the very end and just struggling to fit everything in. I didn't be able to spend quite as much time as I probably would have liked, dwelling on the ideas of blending and make or buy decisions from those operations management topics that were at the end of the lecture. I intentionally usually put a less weight or less content in the week leading up to an exam. Just because I know you guys will want to obviously finish this week's content for the homework assignment, but then also you'll start peering into, okay, I've got an exam and I want to start studying there. So I don't want to too much burden you on new content when I know you're kind of starting to gradually shift your mind toward reviewing concepts for the exam. So that's partly why we're going to have a little bit less content this evening. And so you can see the 3 main headings that we're looking at. Data Envelopment Analysis, Revenue Management, and some more portfolio stuff toward the end there. All are great applications of linear programming. And so let's just go ahead and jump right in. DEA or data development analysis, that may be a new topic for you depending on your background. And so DEA is all about this idea that I have these things operating in parallel. And so you can think of these things or entities as maybe individuals. So examples that I can think of are at H.U. Williams, they've got the idea of a regional sales manager. And so obviously by the name suggests, you'd basically have these people that were in charge of certain segments of the company, or excuse me, segments of the country. Maybe it's like the Northwest, the Southeast, the Midwest, those type of things. And they are trying to drive sales in their respective geographical region. Well, that's great. They're all kind of doing the same thing, right? They're all trying to sell H.U. Williams products, and they're operating in parallel. They're doing it at the same time. They're just doing it in different neighborhoods, so to speak, geographic regions. And so one may ask the question of, okay, is one sales manager performing better than another? And so that may be able to be judged in a lot of different metrics, right? If there was only a single metric, it'd be pretty easy, right? If you just said, well, all I care about is top line revenue, that would be fine. We could very easily determine who's generating the most revenue. But then you may also ask, well, there are different inputs, right? Maybe one region of the company has more people, higher population, like the Northeast would have more people than the Midwest, conceivably. So I'd expect for them to have more sales in the Northeast than the Midwest, potentially. They're correlated between revenue and total populations. And so you now have to start adding a little bit of complexity because although somebody may be generating more revenue, they may have more people to be able to do that. So maybe you start doing that as a per capita in that sense, possibly, as far as dollars of revenue per person, essentially. That would be one way to attack it. We're talking about a little bit more complexity. But then what if there were multiple inputs and multiple outputs associated with it there? Now all of a sudden, then I've got a more complex situation, right? Because now it's not an easy comparison from one parallel entity to the other. And so that's just where the topic of data envelopment analysis may come into play. Another example that I could think of just around the company that I work for is assembly lines. Now looking instead of outward at selling, but looking inward toward the company, H.E. Williams operates some manual assembly lines where we've got individuals standing there and there's products moving down like a moving conveyor belt. That all should sound hopefully familiar to you. And then the idea is, okay, well, are they operating? They're all operating in parallel. They're creating different types of fixtures. They have different numbers of people on it. The tenure or the duration that a person's been to the company is different amongst each person there. So these are all different inputs and outputs that these things could be measured on. And I may be asking the question of, well, is one assembly line acting better than another? Or conversely, you could say, is one assembly line acting poorer than the other as well? And so again, that's the kind of mindset I would like you to have as we walk into the DEA study. And so I've mentioned some examples just from looking at the company that I work for. You can also think of things like restaurant chains, lots of McDonald's, lots of Taco Bells, so to speak. They would obviously acting in parallel. Hospitals, banks, or other things. Our example will actually play in the line of schools. Again, something I'm fairly familiar with just because a lot of members of my family are in education. And so the task we're specifically going to be looking at is this idea of, is a operating unit acting inefficiently there? And like I tried to discuss a little bit before, it's hard to judge that when there are multiple inputs and multiple outputs that I have to quote unquote weigh as I make that determination. And so thankfully, we have DEA as a tool to help us with this. And this DEA problem, as we implement it, you'll see basically solves a linear programming model. And this one's a little bit different than the linear programming models that we've been working with throughout the semester so far. And what I mean by that is that it has a well-defined structure, and kind of this general process on page 209 of our textbook is where it actually lines out this process. So what you'll see is that basically we'll go through this process very much step by step as we go through this exercise that we'll perform in just a few moments. And so let's look at the process. First off, just like every linear programming model we've talked about, we need to be thinking about our controllable inputs, or those decision variables. And the first thing that we'll see in this process is it describes to us what those decision variables will be. They're going to be weights for each operating unit, and we'll be using this to basically determine the performance of this composite unit that we are going to construct. So now think of okay, I've got operating units. I'm going to have a weight assigned to each one. That'll be my decision variable. That's great. One of the things that I'll need to do is make sure that all my decision variables sum to 1. So think of all these as fractional weights, if you will. That's a pretty easy constraint to write. And then 3 and 5, I guess, are the next ones that I'm really thinking about. But 3, let's just go in the order here. For each output, we want the output of the composite unit to be greater than or equal to the output of the unit being analyzed. So again, we're having this idea of a composite operating unit. We're going to have to compute the output of it. And then also we're going to specifically grab one unit to be analyzed here. So with DEA, basically, let's say there's 4 different units. What you're going to do is have to ask the question of, I'm going to pick one of those units and be able to ask, is it operating inefficiently? And then run the analysis. And then if I was interested in all four of them, I would then have to restart the model again to pick a second unit, a third unit, and a fourth unit there. There could be all the different models that we'd have to solve. And so we'll have a set or a class of constraints to model the outputs. And then if I can sneak down here to number 5 here, I'm also going to have a set of constraints to model the inputs there. And getting back up to 4, we have another decision variable, E. This is going to be common across all of our DEA problems. It'll be called the efficiency index. And really at the end, we're going to be judging off of this efficiency index. Basically, you can see from here is a fraction of the unit to be analyzed input to the component's input. That's great. Our objective function is to minimize E. So again, this is a very structured process. So I'm basically telling you the parts of the model that we'll see. And then number 5 is we're going to be writing a constraint for every input in such a way that the component's inputs are less than or equal to the unit being analyzed input there. Okay, so we walk through this process. We say we solve the model. What do we do at that point? Well, we need to interpret the results in some meaningful way. Well, here's our rules for interpreting the results. If that E value is greater than or equal to 1, it does state that the unit being analyzed is acting relatively inefficient. Oh, excuse me, no evidence. There it is. No evidence that the unit being no evidence to suggest the unit being analyzed is acting relatively efficiently. So we can't say that it's acting inefficiently, basically. Where E is less than or 1, there does exist some evidence suggesting that it is acting inefficient. And we'll reinforce that here as we move into the example. All right, so the example, we'll pick schools here. Let's close that real quick. And so our schools here will have 4 different schools. So it looks like they're supposed to be elementary schools: Alton, Beeks, Cary, and Delancey. And then, as this problem would guess, we've got multiple inputs and outputs. We have to worry about it. Inputs in a elementary school setting: teacher to student ratio. That's obviously a big deal. Supplementary funds per student. That's a big deal as well. Average education of parents. Yes, those are all contributing factors of how I would guess a child would perform on some sort of standardized testing, for instance. These are also not all equal, as far as different schools have slightly different populations, depending on how the boundaries are drawn. So that makes sense. Supplementary funds per student. Yeah, that's definitely going to make sense. Like in the city that I live, basically, there are some schools that are set up that are in more, I'll say, affluent areas than others. And so like the PTA, the other supplementary places that have more parent involvement, definitely generate more funds per student than others. Similarly with average education of parents, you can see that as well in socio-demographic regions in a city, for instance. And so the key takeaway is I've got 4 different schools. What I have highlighted here are all inputs to how the school's performance would be affected. And then on the right-hand side, let's say they take some standardized testing, good, better, otherwise, it is a metric to be measured upon. And I have 3 different subjects: the reading score, math score, and history score. And we're just taking the average of the students there. So the big question with all this building up is, I'm looking at the Delancey school, and I want to ask the question, is the Delancey school acting inefficiently compared to the other 3 schools, Alton, Beeks, and Cary? And again, this is complex because of the fact that I have 3 different outputs that I'm trying to consider and 3 different inputs. And so with that being the stage, let's kind of split the screen here and start writing with the whiteboard and building out this model. As always, if you have any questions, feel free to unmute yourself or put something in the chat. So we're at 5.1, and we're looking at DEA. So the first thing to look at is the decision variables. So I'll say let. And what are our decision variables? Well, if you remember, we're going to basically create decision variables that act as weights for each of the parallel operating units that we'll use to build into the composite. And I guess if you will, let me step away one moment here to fix something. Give me 1 second. Okay, sorry about that. I am back. Had a slight issue with the fireplace to take care of there. All right, so as I was saying, our decision variables represent weights associated with the parallel operating units, while our parallel operating units are Alton, Beeks, Carey, and Delancey. Weights here starts with a W, so instead of using X for my decision variables, maybe I use W and subscript them with each of the first letters of my school. So I'll say, let W sub A be an element of the reals, be the weight for Delancey, or excuse me, not the weight for Delancey, the weight for Alton. WB, be an element of the reals, be the weight for Beeks, WC is an element of the reals, for Carey, WD, element of the reals, and that's for Delancey. Also, while we're at it, we'll have the efficiency index in here as well. So again, those top four are coming from the parallel operating units, and then the efficiency index is something we will always have in these problems. Okay, so now that we have that, the next part is the objective function. It's probably the easiest objective function that you're going to see because we just tell you it's the minimization of that efficiency index. So let's say I want to minimize E, subject to some constraints. So the constraints, maybe if I first look at here at our process, I'm looking at item number 2 right here. I need to sum all these weights so that they must equal 1. So that's a fairly simple one to write. I'll say WA plus WB plus WC plus WD must equal 1. Very good. Then let's just go on to the next one, I guess. Item 3 is what I'm looking at here, and I'm writing a family of constraints for the outputs of the schools. And so with that, I have to compute the output of the composite operating unit and make that to be greater than or equal to the corresponding output to the unit to be analyzed. And so since I have 3 different outputs, average reading score, math score, and history score, then I will have 3 different constraints to satisfy this. And so let's just pick the reading first, and we'll work our way left to right. For the composite operating units, what am I going to do? Well, I'm going to take these weights over here and these values for the reading score, and I'm basically going to form the linear combination of these weights and these scores here. So what I mean by that is I'll take that 86, that's for Alton, and I'll say 86 WA plus now that 82 for Beeks, so I'll say 82 WB, 81 WC, and yes, I will include the 81 for WD. Well, I said that's going to be greater than or equal to there. And then on the right-hand side, I'm looking at the output of the unit to be analyzed. That's the Delancey, so that's 81. And so this constraint right here is saying that the composites output in terms of the average reading score must be at least as big as the Delancey score in reading here. And now I'll do a very similar thing for math and history. So I'll just quickly write those out. So 75 WA plus 72 WB, 79 WC, 73 WD is greater than or equal to 73. And then for the history, so 71 WA, 67 WB, 80 WC, and 69 WD greater than or equal to 69. And these are all for the outs. Okay, so now number 4, we've already taken care of the efficiency index definition. We've also taken care of number 6 on the process by setting that objective function of the minimization of E. So now we're down to just number 5, which, as I was describing before, we're going to have a set of constraints for outputs. We'll also have a set of constraints for inputs. Now these inputs ones, it looks like we're going to have to create a composite units input. So that'd be very similar to like what we just did here, except for with the input columns. And we need to make sure this is less than or equal to what? The resources available to the composite operating unit. And so we'll have a little bit of work to do there. So on this one, we need to first take a input. So let's take teacher to student ratio, form that linear combination again. So 0.06a plus 0.05 B, 0.08 C, and 0.06 D. We're told that the operator here is less than or equal to, so that's good. And how do I write the resources available to the composite operating unit? And so what this is going to do, and at this point I have to start involving E, right? Because you notice I haven't written that down in any of these other ones, is I'm going to actually write the input for my school, in this case, of interest, 0.06, but then I'm going to multiply that by that efficiency index. And you can kind of see that in the definition of the efficiency index. It's determined the fraction of the unit to be analyzed input to the composite units input. So when I do this, what's going to happen is I want to try to make E as small as possible. So what I'm going to do is I'm going to restrict the composite units input as much as possible through this constraint as well as the other two that I'm about to write, while simultaneously maintaining that its output must be better than the school that we're trying to analyze. And so you can kind of see that weighing act, if you will, or kind of hopefully see that mental picture of I'm reducing the inputs to this composite as much as possible while simultaneously trying to push out its output so that it's above the school that I'm going to be analyzing. Because if that is true, and if this E value does become less than 1, that means I'm able to do that with fewer resources than the school of interest that I'm looking at. And so that's kind of the overall picture to think about as we perform this DEA. If you have that in your head, then all I have to do really is to write these other two constraints dealing with the other two inputs. And so those will fall out very simply. It'd be 260 WA plus 320 WB, 340 WC, and 460 WD, less than or equal to 460E. And then on the average education of parents, we'll do, again, something very similar. Again, on the left-hand side, we're creating the input of the composite. And then on the right hand side, we have the input of the unit being studied times that efficiency index there. Okay, so at this point, we're looking pretty good. I'm going to go ahead and continue to emphasize that we need to be writing statements to deal with non-negativity requirements. And then just a note here, these are the ins, I'll say, as in the inputs. Okay, so with that being said, and the model on the left-hand side, is there any questions, concerns with where we've arrived at with model formation? Looks like one in the chat. Let's see here. Oh, all good so far. Very good. Okay, so I guess I'll kind of leave it up to you guys as far as implementation of the actual mechanics of putting this in Excel or in Pyomo. Is there any real big feel one way or the other as far as you want to see it in either way, or are you good just me leaving that and I can just show you the results? Basically, I'm asking the question, do you want me to actually type this out and spend time doing that, or are we good just kind of moving over that and continuing on with the lecture, I guess? If you want to shout out, put something in the chat, or give some sort of feedback, that'd be good. Sure. So like at least one person wants to show in Excel, that's fine. So yeah, I don't mind working it out in Excel, and I will then just kind of walk through the Python steps as well. All right, so if I was going to do this in Excel, first obviously I got to get Excel up and running. And I can't remember if I can elegantly grab this information and put it in Excel. Yeah, that performed pretty good actually. Copy and paste from the Jupyter notebook. So one of the big challenges obviously is working with data on these problems. I think I've mentioned that multiple times, so nice to see when things work out every once in a while. All right, so there is our input data to the problem. Yes, I think that's all the input data that I need to worry about. And so maybe I'll just draw a big black bar here and I'll work on the model down here. And so at this point, probably split the screen up a little bit here and pull this a little farther over. We can see the model on the left and the workbook on the right. All right, so if I'm doing this, first thing I need to do is think about my decision variables. I'm going to have weights associated with each one of the schools, so maybe I pull those down here. But then I'm also going to have this efficiency index E value, so I'll put that there. All these gray cells represent my decision variables that I need to work with. As usual, next I proceed to the objective function. Got some different fonts and stuff going on, but that's fine. We want to minimize E, the objective function there. So again, hopefully straightforward at this point as well. And then I've got the constraints. Constraints, typically I say left-hand side, right-hand side, and some sort of comment. And what do I have here? 3, 6, 7 constraints. I think that's enough. First thing we want to do is make sure that all of my decision variable weights, the weighting ones, sum to 1. So I'm going to make sure to grab those 4, but do not grab the efficiency index here. This is a nice one where it looks like just following the model, I'll have a few greater than or equal to's for the inputs, and then I'll have some less than or equal to's for the outputs. 81, 73, and 69 here. And then at this point, yeah, but make some comments here. This is reading, math, and history. And so on the left-hand side, I again need to form these linear combinations. The way that I've set this worksheet up follows nicely for the use of sum product, just because I can very quickly say sum product here. I will grab my weights here. Again, I got to be careful not to grab that efficiency index. And I will grab, since this is the reading, that range of cells right there. Again, notice to be careful about when using sum product. The shape of those two ranges has to be the same. In this case, it's a single column of 4 cells. And then also the ordering also has to be consistent across those. So notice I've got Alton, Beeks, Carey, Delancey, and Alton, Beeks, Carey, Delancey from the top and bottom there. So you'll have to keep track of that. The fact that I copied and pasted the schools from here to here helped me maintain that consistency. All right, so that looks good. Now I just need to do the similar functionality for both the math scores and the history. Okay. So we're looking pretty good at this point. Maybe get it just a touch smaller. On the inputs now, they're going to be the input on the Delancey times the efficiency index each time. So do something like that. Call this the ratio, funds, and parent ed. And then on the left-hand side, we have more of the same as far as the use of sum product to create these linear combinations. So each time we're creating some attribute, if you will, of the composite school in this case. Okay, so at this point, I think we are in good shape. So at this point, we go to data solver. We have an objective function, that's the big yellow one. We want to try to minimize that, minimizing the efficiency index again. We are allowing it to change all 5 of those cells, the weights plus the efficiency index. Then I start adding in my constraints. First one's an equality to make sure all those weights sum to 1. Then I have my greater than or equal to's, which have to do with the outputs. And then the less than or equal to's, which have to do with the inputs. Make unconstrained variables non-negative, that sounds appropriate. And then we want to use that simplex LP solver. So I'll go ahead and solve real quick. Don't know if I'll need them or not, so I'll just grab the reports as well and hit OK. Okay, so the solver's reached an optimal solution, and now the time to interpret. Okay, the first thing I notice is my objective function value is 0.91. Well, if I consult my notes, that meant E was less than 1, so that it's this statement here. That means there does exist evidence suggesting that the unit being analyzed, Delancey schools in this case, is acting relatively inefficient to the others. Okay, that may not be a good thing if you're an administrator at the Delancey school by chance, but Again, that's what the data is showing us for today. So that's how you would interpret that specific statement there. And so a few other follow-on comments to this as far as when you look at this, we slide down here. This is showing that the composite score requires no more than 91%, that's at 0.91, of the endpoint resources to the Delancey to match its outputs. And so you can see that a little bit here. Every one of these is the output, right? Excuse me, every one of those. And notice every time that for the reading, it's above. For the math, it's above. For the history, it's equal. So it's at least meeting those outputs. But at the same time, it's potentially under the available inputs of the other one there. An example of this being that the composite school and the funds per student, the Delancey gets 460. That should be from our data above here, yet the composite school is able to meet the outputs, but is only consuming $323 per student. Where are these numbers coming from? The 0.84 and the 0.14 or 15, those are coming from these weights on the decision variables there. And then the 320 and the 340, those should be the funds per student for Beeks and Carey respectively there. And so that's some of the power of DEA. You've now taken something that is somewhat hard to grasp at times, right? Because again, there's multiple inputs and multiple outputs, and created a very formal and rigorous way to judge it. And that's very repeatable and all those other things that are nice about these quantitative methods there. So with that being said, a brief look at the Python code here. Really, there's not a whole lot that's worth talking about too much here or dwelling on it because it's all about the same that we've seen before. I'm creating a concrete model from the Pymo PE kind of submodule that I aliased up here, Pymo.environment as PE, as you can see. Then I create variables on that model object to represent each of the weights and the efficiency index, again, saying that they're non-negative reals. Then down here, I'm starting to apply some constraints. Here's the one where I'm saying that the expression is that the sum of all my weights must equal 1. Then for each one of the outputs, this should be the output of the composite for the reading score, and must be greater than or equal to the readings scores output for Delancey, just a hard value there, similar for the other ones. And then on the inputs, that's very much the same. In this case, this is the teacher to student ratio, I believe. The composite input there must be less than or equal to Delancey's times the decision variable there for the efficiency index. Notice the expression down here, if I jump down to the objective function, is very straightforward. Just expression is to minimize, there's the sense, the single decision variable, and then I go about issuing the solve command for GLPK. And just like I had these values coming off of the Excel solver, here's my 0.91 from GLPK, and then here's the 0, 0.84, 0.15, and again 0 for the weights there. So both the solvers, Excel and GLPK, are matching up very nicely there. Okay, so I guess at this point, I'll kind of open the floor for any questions anybody has as far as we've gone through the problem statement, we've set up the model, we've solved the model in Excel, and then we've also kind of reviewed the Python code to solve the model with Pymo and GLPK. Is there any questions I can answer from the audience at this point? Okay, I don't hear anything right off the top, so we'll just go ahead and keep moving. So I will first save out a copy of this for the lecture notes. Do a little bit more housekeeping here. and move down into revenue management. All right, so revenue management is, to me, a very interesting area of study. If you look at this, we're talking about short-term demand for fixed perishable inventory, or the idea is to maximize revenue. So some of that makes sense to you as far as maximize revenue. Yeah, most people want to do that, so it's pretty common. Short-term demand, okay, so my time axis is not very long. That makes sense. Fixed perishable inventory. Well, most people, when I think of perishable, their mind immediately goes to the grocery store, right? You go to through Walmart, for instance, there, and you look at the bananas, for instance, is one of the ones that come to mind there. Bananas are obviously a perishable food item, right? I've got some in my kitchen right now. Typically in my house, we do not eat them as bananas, but a lot of times we'll make banana bread, and then we'll be at the kind of end of their shelf life, so to speak. But that's not the only place where you see these quote unquote perishable items. Other things you can think of are things like tickets, right? Tickets to events. What I'm thinking of are like athletic events. Not too many weeks ago, we had the Super Bowl, right? Well, if I had some Super Bowl tickets and I could not sell them before the Super Bowl, well, their worth would be not too much, right? As far as the Super Bowl is, let's say on Sunday, if I still possess those tickets on Monday, I can't really do much with them essentially at that point, right? The event's already happened. They're no good. They've extended past their shelf life there. And so there's an example there. The example we're also going to look at, and the problem is in the hotel industry. That's one, again, that's interesting to me as well, especially in the short term. My wife and I, at one point, were looking to have kind of a weekend getaway. We were looking at tickets up at a hotel in Kansas City. Basically, one day they were a certain price. We didn't book them on that date. Literally within 24 hours later, we went to look at it again. We were going to book it. Well, the same room, same package had jumped $30 just over 24 hours. And so obviously that hotel chain is doing some sort of revenue management, trying to determine, okay, pricing over an axis of time for given hotel rooms there. This actually all came apart as far as who really started this idea of revenue management, not in the hotel industry, not in the food industry, but actually in the airline industry. That's kind of where I'm highlighting American Airlines down here. You can see this job title. I don't know this person, Matt Morgan, but at one point I was perusing around LinkedIn and so that he was a revenue management analyst. And so I thought, hey, this fits very nicely. That he is doing basically as a career, a full-time job, what we're going to talk about for the next probably 15, 20, 30 minutes, essentially. And so think of airlines. Well, that's another place where I have a perishable inventory, right? I've got a plane. It's going to go from, I'll say, Kansas City to Chicago. We'll say fairly short flight there, but that plane has a certain amount of inventory of seats. They are perishable as well, right? For instance, if that plane takes off and there's an empty seat, that's a loss of revenue potentially, right? And so I want to try to maximize the utility, maximize the revenue that's generated for every seat on that airplane. Airplanes are expensive to operate, right? It costs a lot of money to get a plane up in the air across the country and back down again there. So I have to make sure that I am getting as much revenue for every seat in the plane as possible. So inside of this, as you could guess, and so the class is quantitative decision making, since we're studying linear programming, then we can develop a linear programming model to help us determine some of these things. And so with that idea, let's come down to our example problem. So here we'll return back to that hotel industry, look at a specific hotel. In this hotel, basically we're trying to manage the hotel, we're trying to set pricing for a specific couple nights here in the future, we'll say. Sometimes hotels will host a conference or a convention. And then when they do that, there's usually certain deals, right? You have rates for the public at large, but then also it's the idea that if I host a conference and you're attending the conference, you can get kind of special rates for the conference that's being hosted at the hotel itself there. And so that's kind of the scenario we have here. We've got a weekend that the convention or conference is going to take place. and I'm selling rooms to both people that are attending the convention and rooms for people that are just in town, so to speak. Whether we're looking at a Friday and Saturday night. And so one thing I can do is purchase a 2-night package, which covers both Friday night and Saturday night. Notice the convention one is what, $70 less than the regular $295 for the package itself. Or I can just buy a night that's a convention guest. Maybe you're not staying for the Saturday night, maybe you're going home Saturday evening, and so you just pick the Friday night that's $123, whereas a regular person buys $146 for the same type of room. And then Saturday has a similar idea as far as a discount for only the convention people versus the regular people. So we've set the pricing for each one of these types of packages, if you will, right? A combination of a type of guest, whether they're purchasing it through like the convention website, potentially that's how you know it's a convention person versus a regular person. And then also we need to look at demands. At this point, maybe you do a little bit of forecasting and say, okay, for this type of season, I expect a certain amount of volume of people just coming here in general, but then I also have a certain volume that's going to be coming for the convention. And so I've got a projected demand for each type of reservation for the 2-night, the Friday night, and the Saturday night only. So that's all good. And then also I have to have some physical constraints here, right? I've got a hotel, a certain building, there's only so many rooms. Let's say there's 96 rooms in that hotel. And there's also a condition that's being made. Maybe you made a condition with the people that were organizing the convention that 50% of the available rooms at any given time must be available for convention guests. So at this point, they turned over to you and basically asked the question, how many rooms do I need to allocate for each type of reservation? Okay, so with that in mind, let's go ahead and split our screen over again and start thinking about how this could be built into a linear programming problem. All right, revenue management. So as always, we need to think about decision variables. The decision variables here obviously aren't quite as well highlighted, I guess I should say, require a little more thought than with our DEA problem. And so one thing you have to think about is the different types of reservations that you can apply for here. And so I've got reservations for convention and regular, but then I also have 3 different packages which talk about either you're staying one night or both nights. And so looking at this table, you can basically think of this as kind of outlining the decision variables. I'll have to have a decision variable that talks about how many rooms to allocate for convention and 2-night guests, how many rooms to allocate for convention and Friday night, convention Saturday night, and similarly with the regular. And so to do that, you then have to think about nomenclature as far as how you're going to describe these things. And so probably what I would suggest doing in this case is thinking about first sets and then being able to have decision variables that have multiple subscripts tied to them. And so what I mean by that is if I think of the sets of this problem, I have a set of convention and regular, so I'll say it's a guest type. Let's say it's the G is for guest, and it's a set. And I will say that it'll be either a C or an R, where the C stands for convention, and R will stand for the regular. And then I have to think about the duration of the stay. Maybe I call that capital D. So how are we going to describe tonight, Friday night, and Saturday night? Well, you could come up with whatever makes sense to you. One of the things that I think about when I think of days of the week, I do stuff with Python. I've always inferred that Python has a datetime object, and then they have what's called a weekday method inside of that. And so basically, for any given day of the week, like today, you can say I have a date object that was February 20th, 2025, and it knows that today is Thursday. How does it describe Thursday? Well, typically it's a series of numbers, 0 through 6. And I believe, if I'm thinking right, 0 is for Sunday, and 6 would be for Saturday, potentially. Let me look at my notes here. Oh, no. Well, let's see if we can figure this out first quickly. So like that would be able to tell me it's today, and today looks like it's the 3rd there. What I'm doing is basically saying, okay, today is Thursday, and when I call weekday, it's 3. So Friday would be 4, and Saturday would be 5 there. And so I'm going to actually use those numbers to do this nomenclature. And so what I mean by that is I'll say I have a Friday night only. I'll call that 4. Saturday night only, I'll call 5. And the 2-night package, I'll call 4, 5. That looks like 45 here, but I'm really saying that is 4 and 5, as in Friday and Saturday. So just to make sure my notes again on this. This is Friday. That will represent Saturday night stays. This will represent the 2 nights. The reason I'm doing that is because I want to basically be able to have decision variables that make sense to me as far as when I'm writing them. And so now I can come down here and talk about my decision variables. I'll say let x sub, what do I want to start with here? Let's start with the guess type. G comma D, we'll say it's an element of the reals. Again, this is a case where we're using real decision variables for our models, but in reality, we would probably want these to be integers, right? Just because the way the problem is, because I'm going to say these are the number of rooms, I can't have a fractional room. X sub G comma D, the element of the reals. For every G, an element of big G, and for every D, an element of D. And this is going to all represent quantity of rooms allocated for guest type G and duration D. And I'm doing it for every combination. So as an example, I would have X sub C comma 4. That is going to determine the quantity of convention and Friday night only rooms. Again, just looking at notation wise, here now I have a subscript. Each one of, or here I have a decision variable. Each subscript has to deal with a certain set. That are all elements of the reals. And this notation here basically allowing me to say, okay, I'm grabbing everything from a little g, that's an element of the set big G, which is defined up here. And then for every D is an element of D, which is defined here, every element in that big D set there. if you look at it, there's 2 guest types, there's 3 different durations of stay, so there's basically 6 different decision variables that I'm describing in this point. Now we will look at the model itself. So I guess at this point, any questions as far as notation? Okay, I'm not hearing anything. Any thoughts as far as the model? We're usually at the point where we talk about the objective function. Any thoughts on just what we're trying to optimize or how that would be written as our decision variables? Okay, not hearing anybody jump out there. So I guess the thought here is we're doing revenue management. One of the things we want to do is maximize our revenue. So I'll start off with the sense of maximize. And what would be the total revenue that I would incur over this 2-night period? Well, if you think about it, it's just going to be the quantity of rooms for some sort of combination of guest type and duration stay. And I would basically take what in Excel would be like a sum product action of this table and our decision variables. Fairly straightforward. And so in this case, I will just kind of walk across this first row and then go to the second row and write them as a sum. And so in this case, I'll have 225. That is the revenue or the sell price, the revenue generated for every convention and 2-night package room. So I'll say that's X. It's conventions that determines the first subscript, and then the 2-night, that's 4 5, right? For the second subscript. And then I can just move right along. So plus 123, again, X convention. Now it's Friday night only, so that's the 4, plus Saturday, so that's 130. X again, we're still on convention, and we're on 5 there. So that's the convention rooms. And now I do the same thing for the regular. So 295. Now in this row, all of the first subscripts will be R for the regulars. And I'm trying to align these as best as I possibly can so that the packages stay aligned with the stay duration and 152. R,5 there. Okay. So at this point, we've got the objective function there, not any questions that I'm hearing from the crowd. So now we move on to the constraints. And so constraints can come in a couple different flavors here. Probably one of the more obvious ones at this point is I can't run out of rooms, right? I mean, that makes sense that I've got 96 rooms shown right here in the hotel. That's a hard stop, or hard ceiling, if you will. But then I have to worry about, okay, when I write that, I have to worry about it over multiple days, essentially, right? I've got the Friday, I can't run out of rooms, and I can't run out of rooms on Saturday. But then I also have this kind of crossover happenings, right? Because the people that are in the rooms on Friday are just the Friday people that are only staying Friday, but they also have to consider the people that are staying both nights there. And so this is a case where a picture might help us with this a little bit. So I think in the assets here, I've got this hotel revenue schedule diagram is what I refer to this as. And so what I've done here is on the rows, I have every type of combination between the guest type and the duration. And in the columns, I have the given days. And so now we can very easily look by day in this case Friday, which of the different decision variables will be at play. This is very helpful when I wrote a writer constraint to make sure that I don't run out of rooms, because I can just walk down that Friday column and just say, well, XC, 45, the quantity of convention guests staying for both nights, plus XC, 4, convention guests for Friday only, plus XR45, plus XR4, well, that's got to be less than or equal to my total number of rooms in the hotel. And then we do a similar thing for Saturday. So again, this is basically hotel capacity that I'm working against. Okay. Next, we look at some other constraints. Probably within that same sentence, at least 50% of the rooms must be available for convention guests. And the way I'm thinking about that is, okay, I've got Friday and Saturday. On Friday, I need to allow 50% of the rooms to be available to convention guests, and that's an at least, so that's a lower bound, if you will. And then same thing for Saturday. So in that case, I still can use this diagram to help me, but really I'm just interested in the convention guest here. So in this case, the convention rooms that are happening on Friday are these two rows, if you will. So I've got XC45 plus XC, 4. These are all the rooms allocated to convention guests on Friday. Well, it's an at least, so we said greater than or equal to there, and it's 50%. So I'm writing that as just 96 divided by 2, or 48. That's where I'm getting that number from. And so that makes sure that at least 48 of the rooms are eligible to be taken by a convention guest on Friday. And then I do write the same thing for Saturday. So now I'm just moving over to Saturday. It's XC45 and XC5 now. And again, 50% or more on Saturday. So this is the convention room requirement. Move this out a bit. So I think looking at the data, the problem, we've worked on this, that went to the objective function. We've got a few constraints that have came out of that sentence. We haven't touched the demand though, it looks like. And so in this case, we've got what? Projected demand for each type of reservation is shown below. So we're projecting that the convention 2-night package, we're thinking that 40 people could potentially want that type of room. Similarly with all the others there. And so in this case, one of the things we can look at that as is an upper bound, because we wouldn't want to over allocate, right? We wouldn't want to save off, we'll say 60 rooms for convention 2-night package if we did not think that many people could potentially be interested in that. So we could treat every one of these as a bounds on our decision variable, and that bound being a upper bound there. And so let's go ahead and write that, if you will. So in this case, I would say that these constraints will be very simple, but they're just bounds. So that'd be something like XC45 for that first one that we're talking about must be less than or equal to 40. XC, 4 less than or equal to 20. XC, 5 less than or equal to 15. And then similarly for the others, we'd have XR45 20, XR4 less than or equal to 30, and XR5 less than or equal to 25. All these decision variables have to be greater than or equal to 0 for non-negativity, so that's a little bit different, but that's fine. That's my non-negativity there for all of them, and this is demand forecast considerations. All right, so I guess first, any questions, concerns at this point? Don't hear any. I did an example with Excel just a little bit ago. So at this point, I'll go ahead and do this with Pyomo just to make sure that I'm staying somewhat balanced on that. So I'll just start a new notebook here and put pyomo.environ as PE. That looks good. I'll just call M for the model. So I'll PED.concrete model. And again, we're doing concrete models basically throughout the entire semester because we know all the data at runtime. The other type of model is an abstract model that we just don't have use for at this point. So there's that. Then I need to create the decision variables, and I'm going to keep this all in one cell just to keep from basically having a duplication happen of the model possibly getting mad because I'm trying to name things the same over and over again. So if I was doing this, I would probably do this in terms of sets, but I don't know if I want to get into that today or not. Let's not do that. And I'll just write it a little bit longhand. I just don't want to bite off too much for you to chew on, especially right up to the exam here. So I'll just call this, there's only 6 of them, X underscore R4, if I can write it that way, or C4. See if it's happy about that. So there's XR, there we go, R4 is what I would need. That would be a one. So this would be regular Friday night only. And the reason I wanted to show this is I could do bounds here, and I should be able to set a lower bound here. I'll say none here. It's going to already know it's 0 from the non-negative reals. And then for the top bound, XR4 will have a bound of 30 there. And so at this point, notice how in Pyomo, I'm able to wrap some of the decision variables into, or wrap some of the constraints into my decision variable declaration. So let's say xc45 pe.bar domain equals pe.non-negative reals bounds equal to something here. None, c45 is 40. Friday is 20, and then convention guest is Saturday. Equal sign there. Okay, it's always a good idea to hit shift enter every once in a while and need that execute the cell basically, just to make sure you don't type too much and have a syntax error that you're gonna have to fish out from everything. XR45 is 20. XR4 is 30. I've already done. All right. Here, all I'm doing is just pretty printing the variable just to make sure that I'm seeing something here that's okay. The lower bound is 0 and the upper bound is 25. I'm just kind of getting a little bit of a check just to make sure that I am agreeing with what the model's thinking everything is. All right, so at this point, I've declared all my decision variables. Now I need to work on the objective function. So one easy way to do this is saying m.object is pe.objective. I'll have a sense is equal to pe.maximize and an expression where I would need to type in the remaining information. So I think I can do something like this. Just to create a new line here. And I'll just hard code these at this point. This is where if I was doing this with a bigger number of decision variables, I would need to come up with a better way to do it than to hard code the values in here. And there are ways to do that. It just requires a little bit more advanced things in the Python world that I was trying to kind of shield you from at this point. And here I'm just putting those breaks in here to kind of make it look like what I've got written on the right-hand side of the screen. Just really a stylistic thing, nothing more than that. All right, so then I can hit enter. And this again, I might do something like this, pretty print it, just to make sure that things are looking about like I would expect. So here, notice it's taken the m dots out of everything, and this line here should look very similar to this line here. So 225 XC45, 123 XC4, 130 XC5, 295 X45, 146 X44, R4, and 152 X5. So very good. And now for the constraints, remember we already took care of the demand forecast by these bounds, so that's good. And so now I can write constraints for just these top four. And then let's say this is what? First one looks like Friday capacity. So I'll call it Friday cap. And probably the easiest way is just say m.expression. Something like that to get the left-hand side and less than or equal to 96. And then we'd have n.static capacity. That's the X there. Again, shift enter here would be helpful to make sure we're staying in line. So that's those, and then we've got the convention room requirement. So in dot, I think this is one for Friday, convention rec, or the requirement there. I'm just creating some short property names here. And again, I'm very much typing all this out in shorthand just to let you see the ability to do this. If there was things with much larger sets, it would be very much in your favor to work with the pe.set objects and the parameter objects there, and basically create constraint lists and so forth there. I'm kind of holding off on that. Usually I try to shield that complexity from you guys from the Python side of things until chapter 6 when we start getting into network-based models. And then it really is something that shines at that point. But just to know that, okay, I'm doing this very tediously a little bit in some ways. There is other ways too to shorten this type of amount of typing. All right, so at this point, I think I have all of it there. One thing I may be interested in is to pretty print the entire model. And so this kind of gives me a top level view again of all my decision variables, my objective function, as well as the constraints down here. Okay, so that's kind of an optional thing, just to kind of help you troubleshoot potentially. Now I need to create a solver. So solver is equal to te.solver factory, and we need to tell it what type of solver. Again, the Docker container already has glpk, and then I could say results equals solver.solve the model. And like usual, I like to tee out the results so I can see what's going on with the solver. In this case, I did find an optimal solution. That's great. And I'll just display the model afterwards. I think I told you this before, but basically, PyML passes the model to glpk, the model gets solved there, and then it writes it back to the model. All right. So in this case, what are we looking at from the output of glpk on the screen? It looks like the overall revenue that we could achieve is $25,314 for this 2-day duration. And then what is the plan as far as the allocation of rooms? Well, it looks like here's the value. So the convention 2-night package, we want to allocate 36. Convention Friday night, we want to allocate 12. Convention Saturday, we want to allocate 15. Regular 2 nights is 20. Regular for Friday is 28. And regular for Saturday is 25 there. So that gives us our kind of plan of attack, so to speak, when we go to allocate rooms and start accepting reservations for that Friday, Saturday duration. So I guess at this point, is there any questions, concerns on developing the model that we have on the left-hand side as far as how we went from the problem statement to the model, to the nomenclature that we're using in the model, to the PyMO code? Again, there's not a whole lot of code here. Just looking at line numbers here. It looks like basically 18 lines to find the model, and that includes 1, 2, 3, 4 pieces of white space, and then an expression that I've kind of intentionally broken into multiple lines just so that that bit of code there looks like this right here. So all in all, roughly a dozen lines of Python code to develop the model. And then this right here, this kind of boilerplate, as well as that right there. Boilerplate, basically, just the idea that there's nothing really specific to that code about the model itself, but just stuff you always see in these type of problems. So I guess I'll pause a little bit for questions. Okay, I don't hear anything there. I think this was very similar to what we just wrote through here. Oh, got a question in the chat. Oh, good, very good. And there was a question I believe we wanted to touch on down here. This is the allocation again. Things that I would typically impose on you is there is kind of this idea of a presentation layer, so to speak. So you are in this class, you're learning kind of how to do the down and dirty stuff as far as creating a model and everything. But typically the audience that you'll be presenting this to, unless it's like a technical coworker, may not be interested in seeing it like this, but instead kind of dress it up a little bit. So I would present it in a table, something similar like this. This is a nice style format, kind of similar to the way the data was presented to us, giving us the plan. One of the questions that may come up with this is assume all regular customer Saturday nights, so regular customer Saturday night rooms have been sold out. Okay, we're accepting reservations. We've sold out all of the 25 of them. Another customer calls to request a Saturday night room only. What is the value of accepting this additional reservation? So if you think of this, this goes back to our chapter 3 discussions as far as the Saturday night only demand. In my PyOmo code, I basically used a bounds in order to do this, so it may be easier to look at in terms of my model that I've written on the right. We're regular and we're Saturday night, so regular for the first subscript, Saturday night. This one here is the 25. It's basically asking, okay, they've all sold out. We're at 25 on the left is equal to 25 on the right. I get another request. Well, that comes back to part of sensitivity analysis that we talked about. And we're talking about the idea of modifying the right-hand side of a constraint, in this case going from 25 to 26. If you can remember back to that, I mean, this is a good review. We're going right into the exam of next week. That was called what? That was called the dual value. That was called the shadow price of that constraint, right? The idea is how much will the objective function change if I increase this value by 1 unit? This falls very nicely into this discussion because that's exactly what we're asking about doing. Well, how would you do this? Well, in Pyomo, you'd have to do a little bit of work, right? Pass some parameters in there too. Fish out the sensitivity report. In Excel, you basically expose the additional tabs there. Without going through that, you can consult the lecture notes because I think I have lecture notes where the Excel file is actually embedded there in the zip folder that I usually give you. But what you would see in Excel is the shadow price value for that room is $50. So basically by increasing that right-hand side, basically accepting the reservation, we would expect in the optimal solution that the maximum revenue would actually increase by $50. Given the context that we're talking about this, this is known as the bid price in revenue management terms, which the bid price here basically follows the same idea of the shadow price or dual values when you kind of step it out from revenue management and look at linear programming as a whole there. So again, just a kind of nice little tangent type question that you could entertain with this problem. So again, as I save this file off, is there any questions, concerns over revenue management? Okay, I'm not hearing anything big there at this point, so if it's okay with you guys, so I think we're doing relatively good on time. Let's go ahead and take a short break. And I will get my countdown timer. Don't remember what we said that last. Let's just do 8 minutes. That'll get us basically 5 till. And we'll continue on at that point. So there's our timer. And I will see you roughly at 5 till 6. Okay. There we go. All right. I think you should be able to hear me. If not, definitely put something in the chat. So let me clean this up here. We no longer need the countdown timer for this. And that can be just close in the background. And I've already saved off our revenue management. Very good. All right, so as we move from revenue management, now we move into a little bit more of a finance geared discussion to close out the lecture. And so portfolio models, asset allocation, this is one that we've talked about before. I guess we're going to do a little bit more formally possibly this time. Asset allocations, again, similar to the idea. I've got a fixed amount of funds. I've got multiple investment options, stock, bonds, mutual funds, whatever they may be. And I am trying to optimize the portfolio. And so this is where tonight we'll really hone in on the idea of optimize a portfolio. What does that mean? Fundamental things are, well, I want to usually maximize the return I get on a portfolio. I want to minimize risk through potentially diversity. So how do I go about doing that? And we'll actually look at two different examples or portfolios. We'll look at something called the conservative portfolio as well as the moderate portfolio. As you can see, just on the screen right now, a conservative portfolio is going to have the goal of minimization of risk, whereas the moderate portfolio, we're going to allow a little bit more risk to creep in with the hopes of a higher return. And we'll actually see that throughout the lecture examples here, because I'm going to use the same input data for each one, and we'll see the rate of return will increase a little bit, potentially with the moderate one. But of course, it also exposes the user to potentially more risk there. And so this conservative one, we're trying to minimize risk. So think of this as a kind of it says conservative here, but I almost think of it as a very pessimistic outlook on life. So basically, we want to make the best of a rainy day, so to speak. By a rainy day, we're assuming that we're going to have the worst possible outcome happening, and then we're trying to maximize that possible outcome. Depending on how you say that, there's this idea of a maxi-min model here. And this is common term across some linear programming in this area. And you can see it's just maximizing the minimum return or a set of scenarios based on some historical data. And so with that in mind, let's kind of creep into an exact example. A few years ago, I basically went through and grabbed a subset of stocks. So these are actual companies, Caterpillar, Jack Henry, Garmin, Johnson Johnson, McDonald's, Walmart. I'm sure you've heard of them. And we are basically looking at their year-over-year performance of those stocks. And so you can think of the returns as what's embedded in this table. This is data that's actually from actual years, essentially. And so the idea here is that we've got, what is there, 6 different stocks here to pick from. And we have 6 different years here. And so the idea is we have monitored these past years, and we think that the next year, we'll say 2025, we think is going to behave similar to one of these 6 years. I'm not exactly sure how it's going to fall, but we think that one of the 6 years is going to be a good candidate of how 2025 is going to roll out. With that being said, how should I invest? Let's assume that the problem here is not giving us any dollar amount. So we'll just take that as fraction of the total investment. And so if I have a certain amount of funds, how should I distribute those funds across these 6 different companies? And so that's how we will phrase our problem for the evening. And so similar to our last example where we emphasize the use of sets, let's go ahead and do that again for tonight. And so with that, I will go ahead and switch over to the whiteboard. And so I can just talk as I write through these things. We're going to need some sets. So what are the sets? Well, we've got two different really things that we're talking about here, right? We've got companies and we've got years here. Let's say the set of companies. C, and probably a natural notation for these would be the stock ticker abbreviations of it. So we'd have like CAT, we'd have Garmin, GRAMN, Jack Henry, Johnson & Johnson, McDonald's, and Walmart. Again, I think it's an awfully overlooked idea, but just the importance of naming things well, essentially, as far as what are my decision variables going to be, what are my sets going to be, how are you going to describe the entities in those sets. Those things that, I mean, at some point you just kind of overlook them, but then as your model grows in complexity, they become more and more important. The other thing I have is years here. I'm looking at basically the two axes of these tables. In this case, 2017 through 2022. All right. Okay, so with this being said, we've got some sets. Now we move on to decision variables. Probably the most obvious one when we talk about decision variables here is the idea that I need to be able to determine how much of my investment I'm going to distribute to each one of these companies. So we'd have something like let X sub, now we got to think of ordering of subscripts here. Let's do company first and then the year. Oh no, I don't have a year. I'm doing the same investment here. Just keeping straight here in my mind. I'm saying that in a given year, next year, I'm going to distribute certain funds to a company. So I don't need a year secondary subscript. I just need the first subscript here to be the company. And so this would be an element of the reals. This would be the fraction of investment to company C. And this is for every C in the list of my set C here. As soon as I say fraction of investment, probably one of the things you're thinking of, hopefully, is that, okay, I've got to write a constraint that all those fractional pieces sum to 1, which would be my entire investment. The other thing that's probably didn't come out to you quite as much when I look at this, it's just more in the description of the problem is I'm trying to maximize a minimum rate of return. So I need to describe that as a decision variable here. And so let's say I've got M, Schnellman arrears. This is the minimum return of the portfolio. Okay. Now that I've gone through this, since I'm going to write this fairly generically, I'm going to also model it after what we'll end up seeing at some point in chapter 6 when we talk about PyMO and how it's set nomenclature. I'm just kind of getting a little highlights of this today, is the idea of parameters. In the PyMO landscape, parameters reflect the data itself. So the major block of data that I see are these annual rate of returns for every company. And so let's also let that be genericized, if you will, by saying let's let some variable A of sequom y be an element of the reals. And this will be for every C, which is an element of C, and for every Y, which is an element of the big Y there. And this is going to represent, let's keep it in black, the rate of return for company C, so the lowercase c, in year Y. So as an example, if I said something like X of MCD, comma, 2019, the value would be what? 0.122401. So basically think of, now we have a way to, as a variable, describe every number that we see here, all those floating point numbers. Go ahead and blow the image up a little bit here. All right, so now the model. Well, I've kind of hinted a little bit at the objective function here, where it says maximize the minimum return. And so we've already described a decision variable up here that talks about the minimum return here. So kind of similar to DEA, we're going to have a very simple objective function, which just says maximize that in value. Subject to some constraints. I think the first thing I said before was, as soon as I say up here a fraction of the investments, I want to make sure all those fractions sum to 1. And so I could write that out, x of c, x of cat, x of Jarman, x of Jack Henry, x of Johnson & Johnson, dot, 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 all the way sum to 1. Or if I wanted to embrace this kind of more mathematically advanced, I guess I'll say, for lack of a better word, notation, I can say something like, well, if I sum up for every c, which is element of the big C, all of my x sub c fractions, that's got to sum to 1. And I'll just say, as a comment, fractions of investment sum to 1. Okay, so that's good. And then the next statement is going to have to do with the annual rate of returns of my investment. And so what do I mean by that? Well, let's take a year. Let's say take 2017, for instance, and think about the idea that I've now got decision variables x sub c, which discuss how much I'm going to invest in any given company. I would expect the overall rate of return for that portfolio, given the candidate year 2017 occurs, as the linear combination of the fractions, the x sub c decision variables, and the data points in here, the annual rate of returns of each individual company for that year. And that would be for 2017. And then I would write a similar thing for 2018, 2019, 2021, and 2022 if I was interested in each year's portfolios, each candidate year portfolio's rate of return. And one of the things we're trying to do is we're trying to maximize this in value. So we're going to treat that as a floor, and we're going to try to pull that up, up, up as much as possible on these overall returns. And so how do we write that? Well, we're going to have to write one for every candidate year return. So maybe I'll start on the right-hand side and say for every Y, which is an element of the big capital Y there, I want to make sure that my M is serving as a lower bound, so greater than or equal to. And on the left-hand side over here, I want the return for my portfolio given that candidate year. And so in this case, I've got the year right here. I will then sum, like I did before, across all of my companies. And I now need to not only have x sub c in this here, but I also need to multiply it by my parameter a c comma y times x sub c there. And this would be the actual constraint line itself there. And I'll just put attempting to raise the floor of the minimum rate of return. Okay, so those are the two main constraints for this model. Other things is non-negativity, so I can write that as x sub c has got to be greater than or equal to 0 for every c, which is known in the company c. So basically, it's either I invest 0 or some fractional amount. I can only invest up to 1 because of this constraint here on any given one. And the other thing I want to enforce here is that I've got a decision variable m. And notice how m here, I'm not saying that m is going to be greater than or equal to 0. Why? Well, I'm making the statement here that even on a very pessimistic outlook of this, is the best of all the pessimistic outlook could still result in you losing money conceivably, right? That would make technically good sense, right? That the outlook may be just very, very poor into the future, and I'm just trying to minimize the losses that I'm going to take there. And so that may be a slight disagreement if you're reading strictly closely with the book lecture, the book chapter this week. And if my memory is not mistaken, they probably would have a greater than or equal to there. And I just fundamentally disagree with that because of the statement of that it is possible for you to be losing money there. So with that being said, is there any questions over kind of the ideas of this model as far as this being conservative? You're trying to make the best outcome over a very pessimistic outlook, and that's where we see we're trying to maximize this minimum rate of return, and that really is happening through this objective function and this series of constraints, where again, every one of these year scenarios is a candidate year that we think the future will be like. And then this on the left-hand side is the resulting return of your portfolio after you've invested a certain amount of funds into each of the companies. Okay, I don't hear any immediate questions, so if you'll allow me to just kind of peek through some of the code here. This is the model type stuff that's very similar to what we looked at. One thing also just to point out here, I've used capital M this evening as a decision variable, the minimum return for the portfolio. One of the things I always encourage you guys to do as you're going through this class, if you have time, is to kind of peruse other literature associated with the subject area. There's a lot of great stuff out there for different examples and so forth that you can take a look at. But if you're doing that, do be aware that there is something called big M notation, which is different than what I'm doing tonight, I guess, in short there. Big M notation, we'll get more into things in the coming weeks when we talk about kind of like binary decisions and some more different modeling topics there. But if you hear big M notation and you see a capital M that looks kind of like that, know that that's a slightly different thing or concept than what I'm talking about tonight. But anyhow, there's this. Also, I mentioned before a little bit of other things as far as with Pyomo. This would be a great example of that I didn't want to get too deep into typing the complexities of it out. But here I'm taking data from a CSV file. This would be fairly real life, realistic potentially. Especially if you didn't work in IT and didn't have access to a SQL database potentially as a data store, they may give you a CSV file and you could read it into what is called a pandas data frame. That's what's actually getting printed here. But notice I can then use that pandas data frame with this variable here to glide right into the model that I'm creating here. Without getting into too much details, basically I'm creating a dictionary where the keys are Python tuples, one for the company, one for the year. That's trying to model this subscript right here, the C and the Y here. And then this year data sub C is going to be like that 0.122401 there. Now I'm creating a concrete model that should look familiar to you. Companies and years. Now I'm introducing the idea of a Pyomo set. Similarly, I'm introducing the idea of a Pyomo parameter. And I have to be very careful with this line a little bit, just because parameters here, the first few arguments here that are not initialized with the keyword, those are anticipated by the parameter object as indices. And so this is going to be indexed off of my companies and my years that are my sets of my model. So that allows me to, again, set up that C and that Y subscript. And then I'm initializing it with a dictionary here, which matches in terms of the indices. So the fact that that dictionary has a key value that is company, comma, year, and this says company, comma, years is not accidental, but is intentional there, and that's how everything gets aligned. Variables here. Now I've got a PE.var. Usually I've just did something like, well, that's a non-negative real. Notice tonight I'm also putting, again, another argument to this, where this is the index that's represented by this variable. So notice up here I said x sub c. Well, that's the C representation here, because that model.companies is defined as a set. So now it knows that the PE.var is a indexed variable, with that set being the index. M is the minimum rate of return. Notice it's no index, so I can say it as usual. Also notice here I'm saying PE.reals, not the non-negative reals, to enforce the idea that it can become negative. The objective here is very straightforward, considering the simplicity of the expression. And then here, I did mention this before. Notice in this one, for my unity one, that's this first constraint. It's very similar to what we've done before in the sense that it's one line. It uses PE.constraint. The expression is slightly different here because I'm doing a kind of an inline for loop with a summation wrapped around it to basically sum all of my decision variables. I'm setting it equal to 1. But then also I mentioned some of the stuff that you can save time, so to speak. Notice here I've got a bunch of different constraints here, right? This line right here is actually describing, I think, 6 different constraints, one for each of the candidate years we're looking at. And so to do that, notice I'm not writing 6 different lines of Python code, but I'm just writing 4 different lines of Python code technically, one to set up my constraint list object, one to index over the years, that's this part right here essentially for Y and model the years, and then notice here I'm computing the left-hand side. This is using that sum here at the inline for loop, very similar to what I did down here, but then I say, hey model, I'm referencing a constraint list here called candidate year returns, add an expression in here where the left-hand side must be greater than or equal to the right-hand side there. And so this is how I'm able to then use a very little amount of Python code, because I'm wrapping in a for loop, to enumerate all the different years and then be able to add a constraint one after the other there. Again, don't worry too much about this, especially going into the exam this next coming week. But this is more the kind of power that you can harness with using a tool like Python in order to do this. In Excel, you're kind of you're kind of hamstrung. You're kind of limited by the interaction with that workbook, that spreadsheet type interface there, and maybe things become a little bit more tedious in that nature. But at the end of the day, I can go ahead and solve this model. You can see that optimal solution was found. If I model preprint, I've got a lot more stuff in here now. It actually wants to describe the constraints, or not the constraints, but the sets. And I had that parameter declaration. So notice here, this is what I was talking about. This is the data table that I was looking at. So it's now basically reporting off saying, hey, I know about this thing. And the variables aren't until I get all the way down here. Notice the end goal was to invest roughly 15.8% of the funds in Caterpillar and the remaining 84.2% of the funds in Jack Henry there. This resulted in a minimum rate of return of right here, 4.4%. And I can see the same stuff coming out of Excel. In this case, the Excel one would not be really too much different than usual. I guess I'll go ahead and download the materials we want to look at the second one here in a little bit. So let's go ahead and pull that down. So what does this really mean in terms of the applications of it? We've got this here. I wanted to show you the figure. And so what is this figure, this bar chart at the bottom? Basically, we tried to minimize or maximize the minimum rate of return, and we found that to be 4.4. So assuming that I invest like my optimal solution tells me to, again, 84% to Jack Henry, roughly 16% to Caterpillar there. If any of these candidate years happen, so 2017, 2018, 19, 20, 21, and 22, I expect at worst to do roughly 4.4%. And it happens to happen at both 2018 and roughly 2022 as that. But I could also have a good year if 2017 happens to be the closest to what's happening next year. Then notice I get a rate of return of roughly 37.2%. But again, the whole objective of the conservative portfolio is to try to grow these smallest ones as much as possible there. And so that's how we arrived at the model that we looked at. So before moving on to the moderate portfolio, is there any questions, concerns from the audience at this point? Okay, not hearing anything there, so I guess we can go ahead and move on. So the moderate portfolio is very similar to this, except for now we are to accept a little bit more risk. And what do I mean by that? Well, is we're going to give the model a little more flexibility, if you will, and the hopes that it generates a higher expected value of the return, with knowing that, okay, it is possible that I may end up with a return less than that 4.4% that was in the conservative model. And so one of the key things to notice there as I'm talking is that now I am looking at this expected value of the returns, and I'm trying to maximize that. So when I say expected value here, I would like you to think about some other classes you may have had, specifically probability and statistics potentially, where we talked about the expected value of some random events essentially, where really you're having this idea of the probability of something occurring times the outcome itself there. And so that's one of the concepts that we have to now introduce into this model. And so with that, we're also going to set a minimum rate of return, so of in this case of 3%, just glancing down here. So what I mean by that is we've changed the objective function to try to drive this expected value higher and higher, while at the same time setting some floor to this expected value as well. And so let's take a look at the kind of mechanics of this. At this point, I'll just skip the writing it down on the left and just kind of talk to the slides, if you will. So we're going to set a minimum rate of return of 3%, and we're trying to achieve a moderate portfolio. In this, we're going to use the same stock data set. So again, the same data set that we're seeing right here. This is the input data that we're looking for. Same candidate years, same companies, same historical data. And so what do we need to do? Well, one of the things we need to do is be able to understand this idea of an expected value. And so to do this, one of the things I'm going to do as I slide down here is create this idea of a lumped variable, if you will. And so what I mean by that is we still have the same decision variables as last time, per se, with the exception of this M value. That is no longer a decision variable. We're actually going to be setting that to, in this case, 3%. And so the X sub C, though, that is the same, as far as that is the amount of the total contribution of funds that we are allocating to each one of the companies. Well, we need to calculate the expected return for any given candidate year. Well, for that, we need to know some probabilities. That's not given in the earlier data set. So I'm just saying right here, each one of the candidates' years is equally probable. There's 6 candidate years. So we'll say the probability is 1/6. That's somewhere around, I believe, 16%. And so something that's a convenience feature is to create this kind of lumped variable here that I'm calling R sub y. And there's actually 6 of these, one for each year. And notice what I'm doing is I'm basically creating that lumped value to be the holder of the expression of this linear combination. Basically, it holds the left-hand side of what was our constraint here for our conservative model, or the anticipated rate of return for any given candidate year given a given portfolio. And so that's where R sub y is. Okay, why would you do such a thing? Well, one reason you would do such a thing is if you have to reuse that combination of expressions over and over in your model. So as we look down our model, you'll see there's multiple cases where I'm using this lowercase r. So that's the drive for actually creating it. First, you can see it in the objective function. Right here, I'm telling you, you got to maximize an expected value of the returns. So I'm maximizing, well, there's my 1/6 I'm pulling that outside of that summation just because it's a constant across all the terms. If it wasn't a constant, then I would have to have a variable inside of here, which would be referencing the year that I'm talking about, and we'd have to work through there. So this is an R element of R. This is my set of R. It's all these lumped variables here. And so this would actually be a fairly lengthy expression if I was to actually show it there. And so this is a nice, concise way of writing that, essentially. Subject to, okay, we wanted to make sure that any given candidate return is at least as big as the minimum rate of return, the 3%. So imagine that M value is now taking the value of 0.03. And for every one of these R values in here, I'm having to write this over and over again. So now you can see hopefully the value of that lumped expression, because I'm now reusing it first in the objective function as well as in every one of those constraints. The other constraint here is very similar to what we just wrote here, exactly the same actually, and just stating that the summation of all of my fractions of investment have to sum to 1. And then I would cap that off with the non-negativity constraints there. So let's slide down into a little bit of the code here. Here it's very similar Python code, so I don't want to dwell too much on that. Does use the idea of sets and parameters, again, with indexed variables here. And just to get an idea, I mentioned this would be a fairly long expression. By that, I mean, there's the expression itself there. This is part of the reason why I like Pyomo and that concise mathematical bit, because you can see I'm not having to write that much code in this little bit of line here, as far as just the number of characters that define this expression gets evaluated to all of this, essentially. So that's one of the abstractions that Pyomo helps with. Other than that is the similar type of idea, using constraint list and constraints and then solving it and getting to the solution here, which in this case, the optimal solution is slightly different, right? Before, I think we were just using 2 different ones as far as the stocks, but now it's actually saying, okay, introduce what, roughly 14% for Caterpillar, 56% we'll say for Jack Henry, and roughly 30% for McDonald's. Notice the maximized expected rate of return is 14.4%, so that's pretty good. And before I move on from this, I do want to make sure that I show you in Excel a little bit here as well. I just want to glance over that solution method. So moderate portfolio here. Yeah. So the thing I wanted to highlight here is this idea of this lumped variable. There we go. How do you implement this type of thing in Excel? Well, notice here I've got all my historical data. I've got my year probabilities. I've got that minimum rate of return hard-coded there to where I can see this a little better. I've got some sum products between the year probabilities and the lumped constants. And then notice these lumped constants down here. They're sum products of the decision variables and each one of the returns. That's nice. But notice in the constraint sections here, I'm actually just putting the lumped variables. Like this is the R 2017, using this nomenclature, R 2018, 2019, 2021, where these are referencing the decision variables. And then here, I've got these referencing the individual cells there as well. I guess maybe the best way to do that would be to show this type of description here, where this cell is referencing this range and that range, and then that cell is being referenced in the objective function and the constraint there in row 41 there. And so that's how you implement that. It's fairly straightforward as far as how the worksheet works there, but may not be something that's immediately obvious, so to speak there. So I just want to highlight how you can do that in Excel, and then you can save yourself some typing there. All right, and then as far as solution-wise, we should end up at the same results, 14.2, 55.86, 29 point. there. That's good. 14.4% for the maximum expected value of the return. So that's all good. But let's show a bar chart now and kind of contrast this, what we saw from the conservative model. I think 2017 on the conservative model was the best one. It was around 37 or so. Now it's topped a little bit over 40. So we're accepting a little bit more risk and seeing a little bit more return for that best year, so to speak. Hopefully the next year happens like that. But notice 2018 and 2022, last time they were the lowest as far as if those candidate years happened, they had the smallest rate of return. And it was 4.4%, right? That was the minimum, the best of the minimum, so to speak, right? The maximum models there. But notice here, they're at 3%. So this is where we're opening ourselves up to a little bit more risk, right? Because conceivably I could have a 3% rate of return, while at the same time, the expected value is going to be better because I'm allowing it a little more flexibility to chase these more quote unquote risky opportunities there. And so that's just the example here of showing that, okay, a slight tweak in the model between objective functions and constraints can yield you slightly different portfolio options, if you will. As far as an advisor, I guess you would want to kind of gauge the expectations of your client to be able to determine, okay, which one of these things you would want to slide it toward, essentially. All right, so I guess I'll take a pause to see if there's any questions, concerns over either the portfolio models that I'm describing here and kind of highlighting the solution paths to, or really at this point, anything in the lecture as a whole. We've made it to the end of the lecture, the few minutes left that I'd like to talk about the exam in the next part of the lecture. But first, any questions on the content for the evening? Okay, not hearing anything, so I guess we'll move kind of more toward the administrative role of the discussion. I guess first, homework assignment. Chapter 5 is open at this point. You'll have it due in a week. 2 attempts, takes your highest. Only 7 questions here. I did get pegged about showing the preview, so I'll just show that here. Question 4 out of the textbook, question 9 out of the textbook, and that's it. I did mention earlier in the evening that I try to keep the week leading up to an exam somewhat light, so there's an artifact of that, essentially. So same thing as always there. And then the real topic next, I guess, is the exam. So you can see here from my screen that a stub of the exam, I'll call it, is in place at this point. I basically haven't a week in order to kind of finalize it out. But at least at this point, I like to kind of give students a feel for what the exam looks like. It's traditionally what I do in this class. And so I will go ahead and close this. And what I usually do in the week before the exam is I'll show what the exam looks like right now. And so that's what this workbook here is describing. And so what do we have here? We've got a Canvas exam. Basically, the way the exam first will be administered, it'll be administered similar to a homework quiz that you've been doing with probably a couple minor changes. One is obviously it'll take a little bit longer to do than as far as well, I shouldn't say that. One is that you're going to be timed, essentially. Basically, your homework problems, I give you no timer limit once you start the Canvas quiz. You just have the open and close dates, which is basically a week on the Canvas quiz that limits your time. On the exam, it's a little bit different. The exam, you have a single attempt and you have a time limit. What does that mean? Well, it means as soon as you hit start on the exam, you have the timing of the exam to finish it. Just to take a peek at here, I believe the timing should be equivalent to 1 class period, 150 minutes. We meet for basically 4:25 to 6:55. That is 2 hours and 30 minutes or 150 minutes. So you have one kind of in-person class session to do the exam. And I try to gauge the length of the exam, number of questions and so forth, so that they would fit reasonably into that time frame. But again, the key takeaway to begin with is This is a timed exam, so once you start it, be sure that everything's good. You have a solid 2.5 hours to essentially work on it. You don't have any interruptions there. Your internet's good. If you're on a laptop, make sure it's plugged in. All those type of things to consider there. All right, so timing, once you start the exam, you have 150 minutes. When during the week do you get to take exams? Kind of the next follow-on question. I don't necessarily care too much. You can see the start and stop dates here. This is class time in 1 week. This is class time in basically 2 weeks. So starting from next Thursday to the Thursday after, you get to schedule when that exam works best for your schedule there. I've got a mix of online and in-person students there. I know we all have different schedules outside of class, so I want to give you guys the freedom to pick a time slot, a now 2.5 hour time slot that fits your schedule most, that you can fit into the exam, given these two constraints of the available from, until, and the due dates down there. So that's kind of the administration side of things. As far as other things in that level, I do expect you to be kind of doing this exam on your own. Try not to get in a big group and try to teamwork there. I do consider that to be academic dishonesty there. So I am trusting that basically you will uphold that standard, as I would expect you should, as graduate students at PSU. And so I think that's all I'm going to say on that matter. Now to actually get to what you get to use on the exam. I treat this exam similar to the way I treat the homework. I'm trying to prepare you guys to be able to do these things as if you were sitting in the wild, so to speak, the wild out in the field, out in industry. So I am okay if you use your textbook. If you have a different textbook, I'm okay with that, as far as, because I assume that you would have those things at your disposal in real life. Not that school isn't real life, but you know what I'm saying. And then also, I allow you to use the software that we've been using. So what software have we been using? Well, we've been using Excel, we've been using Pyomo with Python, we've used Plotly for some graphing and Plotly. You've seen Desmos that can be used. All these different types of tools that you've seen me use in class, I will allow you to use on the exam itself there. So next comes usually the questions of the content of the exam. And that's kind of the two tables that I've presented here on the spreadsheet. This is the way the exam sits now. It probably won't change too much for the moving forward there. The changes I do make, I'll try to constrain myself to what we're seeing on the screen at this point. But I basically split the exam into two different types of questions. First is the conceptual questions. These are multiple choice. These are true, false. These are simple type of calculations that shouldn't take very long, and they're really testing your conceptual knowledge of the subject area. Putting that into context of what we've talked about so far in the semester, we've talked about, like, what is a linear programming model? What are constraints? What are decision variables? What is an optimal solution? What's the feasible region? Chapter 3 had all the sensitivity analysis type of terms, right? Dual value, shadow price, range of feasibility, range of optimality, right? All these things are things that I would say are fair game for the conceptual questions there. And so you can see the number of questions as well as the total points of the exam allotted to that by chapter there on the left table. Then come the application questions. You can see the application questions are worth more per question than the other ones, and these are more similar to your homework problems. These are questions where I give you a problem statement, and for this part of the semester, I'm looking at you building a linear programming model, solving the linear programming model, and then being able to answer a few questions about that model. So think of those, again, as similar to the setting of the homework problems. That's probably your best judge, or the lecture problems, same idea there. Those carry more weight, and so I do allow you to upload a file or files. If it's multiple files, I think this thing may only give you one, so you'll have to put them in a directory and zip the directory and upload it. And I think the last question of this exam is the way it's set up, so that you can upload that file. Please upload that file. That's your ability to get partial credit, and actually give you, as you can see, a 1 point out of the entire, I think there's 63 points right now of the exam, for just uploading the partial credit file there. So what happens is basically Canvas grades the exam. It's going to automatically grade it. And then after the deadline, kind of like do your homework statements, I basically collect all them. And then I again give you partial credit on just the application questions. My thoughts here is, well, if your application problem is almost perfect. Maybe all you did was you messed up the sense of the objective function, max and min, everything else is flawless, then I can give you most of those points back essentially, because you're showing a good mastery of the overall problem there. So I think that's basically my usual discussion points on the exam. Also, all this stuff I'll reiterate early next week, as far as my usual weekly announcement type thing. We'll talk about the exam, kind of as I talked about scheduling there. A consequence of that is next week we will not have any formal meetings, so to speak. So, like next Thursday, a week from now, I don't plan to be on campus. And I also do not plan to host any sort of Zoom meeting at this point, as far as publicly there. So, take that time to start studying there. As you're studying, if you do have questions, feel free to email me. We can get in touch there. That'd be a great place to say, okay, yeah, I'm reviewing the chapter 3 material. I see this range of optimality. Can we have a discussion about some of the finer points of that? That's definitely open to be utilized up to the point that you start the exam. Obviously, once you start the exam, I'm not going to be able to really help you within that 2.5 hour time frame. All right, so with that being said, any questions, concerns over kind of the next couple of weeks then? Okay, I'm not really hearing anything. Again, if something does come up, just let me know. Best way to get in touch is probably email, and then we can go from there. And so, as usual, at this point, I'll leave the meeting open for a little bit, and if nobody answers any questions, then I will close it after a while. Do you have a question? Are the correct answers to the homework questions posted? Typically, I do not post the answers to the homework questions. I don't know if I've really been asked too much of that in the past by students. If you want, I can get in touch with you on an individual basis. I guess where I'd rather prefer to do that. So I think, Jared, you're the one asking that at this point. I've got your Canvas submitted solutions there. So if you want, send me an email just to remind me. Also, if you would, in that email, maybe attach your homework that you've actually done. I assume you've got some files there, so I can review, and I don't mind basically talking toward or sending an email to reply back, which discusses your work plus the solutions to it there. That'd probably be a good idea for studying at that point. So yeah, I don't mind doing it. I just rather not publish them broadly. Instead, just do it kind of case by case basis. But again, I'll leave the meeting open for a little bit. If you're good to go, then I guess kind of class dismissed. And um, I guess actually I probably won't see you guys for it'll be 2 weeks essentially. I'm hoping to be back on campus and we have some nice calmer weather here, but it won't be next week. It'll be the week after, where we head into chapter 6 after the exam. So with that being said, I'll stick around, and those that are ready to go, have a good evening. Stay safe and stay warm. Do I have a preference between Canvas messaging or email for reaching out? They all go to the same email address. You can go to their Canvas, and it basically pings my other email as well there. So your choice. Okay, so I don't see any other questions popping up, so I'll go ahead and shut down the meeting.